Hi everyone, welcome back to this week's GOCC. Today we have Ariana Chin from UCLA speaking about the classification of Zamolodchikov periodic cluster algebras. Before we get started, let's remind ourselves of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. And with that, Ariana, whenever you're ready.
All right. Thank you for the introduction, Bailey. Um, today I'll be talking about some of the work I've done in the last year. Um, and of course, if anyone has any questions, please interrupt me at any time, because otherwise this talk may be quite short. So let's just get started. The basic outline of this talk is I'll give you a brief introduction to cluster algebras and some other things that are necessary for this talk. Um, We'll dive into my main result, which is the classification, and then go into a secondary result, which is a follow-up that I did this year. And then finally, some pretty interesting conjectures that I hope will interest all of you all. So the easiest way to visualize a cluster algebra is with a quiver. So a quiver is just another name for a directed graph, which for our purposes, we only care about quivers that have no loops and no two cycles. So let's say we've got a quiver. Here's an example of a quiver right here. Can you guys all see my mouse as I'm moving this around the screen? Okay, awesome.
Yeah.
So let's say we have a quiver. It has an adjacency matrix that is skew symmetric, and we can mutate this quiver at any vertex to produce a new quiver. The steps for mutation are we identify all possible length 2 paths that pass through that vertex, and then we draw an arrow from the start to the end. And then we reverse all the arrows that were originally adjacent to that vertex. So if we look at our example right here, we can see that there are actually 2 paths of length 2 passing through our vertex. One is using the top arrow and one is using the bottom arrow. And so we're just going to add 2 arrows going from 1 to 3. Notice that we've also reversed all of our arrows that were adjacent to 2. But now we see that we've got a quiver that does have 2 cycles, and that's not okay. So all we do is we let our 2 cycles cancel out so that we have a quiver that we like, and we are done. Notice in particular that if I were to mutate again at vertex 2, I would actually get back to my original quiver, and that's not a coincidence. Mutation is an involution. Moreover, a mutation is a local move. So notice that every step of our quiver mutation only affected vertices that were originally adjacent to K. That means that if we have 2 vertices that were not adjacent, it doesn't matter whether we mutate one or the other first, they are going to commute. One thing I will note is that someone in a previous talk, someone mentioned that all of the arrows have suddenly reversed from the start to the end. That is a coincidence. In general, mutation can make a quiver much more complicated, and it will not just simply reverse all of the arrows. However, it is a coincidence that will appear in every example in this talk. Okay, so now that we have quivers and quiver mutation, how do we create a cluster algebra from that? Well, first of all, for every vertex in our quiver, we associate a variable, and we call those cluster variables. Together, all of the cluster variables for a given quiver form a cluster. So for our quiver of 3 vertices, our clusters will always be of size 3. We say a seed is made up of a skew-symmetric matrix and a cluster. This skew-symmetric matrix is just the adjacency matrix of our directed graph. And then, given a seed, we can mutate it to create a new seed. So we've done the same mutation as we did in the last slide, and now we've gotten a new quiver, a new matrix, which is the adjacency matrix of that new quiver. and we have x2 prime. So the only thing that happens in the cluster of variables is that the vertex that was mutated gets replaced with a new variable that is related via this exchange relation. So this is just a product over all incoming arrows plus a product over all outgoing arrows from our our vertex K. Are there any questions so far? Okay.
Just a silly
Yes.
question. Why do you need to have also the cluster? Isn't the dimension of B always, or can you have?
So the cluster is the variable. So we're keeping track of the variables at every point in time. We need the variables and we need the matrix. So the variables will change with mutation with these exchange relations. We could mutate and get back to the same matrix, but have our variables be different. So we do need both. Yeah. Any other questions? Okay, so I've sort of been misleading you in talking only about quivers, and actually, there are cluster algebras that are not associated to quivers. So the natural generalization of a quiver is a skew symmetrizable matrix. So remember that quivers are associated with skew symmetric matrices. Now we can define this notion of a skew symmetrizable matrix as a matrix that we can force to be skew symmetric by scaling its rows by some vector scalars. For example, let's take a look at this matrix. This is obviously not skew symmetric. However, if we scale the second row by 3 and the third row by 2, we do get something that is skew symmetric. So this is an example of a skew symmetrizable matrix. Now, we can finally define a cluster algebra. Given an initial seed, which has a skew-symmetric matrix, and an initial cluster, the cluster algebra generated by that seed is the algebra generated by all cluster variables across all mutations. So we start with initial seed. We can mutate in many directions, one for every vertex. So if we have n vertices, we can mutate in n directions. Each one of those will give us a new seed. Now, given that seed, we can also mutate in n different directions. So we can see that we would get this gigantic n regular tree of clusters. Now, in that infinite tree, take all of those cluster variables that will generate your cluster algebra. So it's a very, it's a non-standard way of generating an algebra. And as you can imagine, you may get many, many, many cluster variables, probably infinitely many. In the very rare case that we only have finitely many cluster variables, we say that this cluster algebra is of finite type. Now, in 2003, Fomin and Zelevinsky did classify all cluster algebras of finite type to be the Dynkin diagrams. In particular, if you have a Dynkin diagram and you choose any orientation of that, that will generate a cluster algebra of finite type. So why am I talking about skew-symmetric and skew-symmetrizable matrices? Much of this talk is going to be discussing results that were already known for skew-symmetric cluster algebras, and then we will be generalizing it to skew-symmetrizable matrices. So let's compare. First of all, both of them will generate a cluster algebra. What is the difference in mutation? On one hand, we increment the adjacency matrix entry by the number of length 2 paths. On the skew symmetrizable side, we see that is the same as incrementing by bik times bkj, right? This is just paths from I to k, paths from k to j. In the classification of finite type cluster algebras, the skew symmetric ones correspond to types A, D, and E, whereas the skew symmetrizable ones are all of the Dynkin diagrams. So I've drawn them right here. And we can tell the difference between the A, D, and E types because they are also known as simply laced. In other words, they just look like graphs, whereas the other types have these interesting Dynkin edges, which look like this. There are like double Dynkin edges and also triple ones. So notice that I've colored all of these Dynkin diagrams white and black, or gray and black, because they are all bipartite. We will be working with bipartite graphs for the rest of this talk. So naturally, we will have to generalize the idea of what a bipartite graph is. So we say a matrix is bipartite if there exists a coloring of the indices such that for any two indices of the same color, that matrix entry Bij is going to be 0. And then naturally we can define the idea of a bipartite mutation, mu white and mu black, as a mutation at all white vertices or mutation at all black vertices. Remember that because mutation is a local move, this is a well-defined notion. All of the white vertices will not be adjacent to each other, so we can commute these mutations. Here's an example. We start with some graph that I have colored arrows in a way that is not important right now. And we are going to apply mu white. So there's only two white vertices, v1 and v2. First, we mutate at v1 and we get all of these new black arrows. When we apply v2, we see that we get all of the same black arrows, but oriented in the opposite way. And so they actually all cancel out. And in the end, we get essentially the same quiver, but with all of the arrows reversed. So this is what we call recurrent. If when you apply mu white or mu black, all of the arrows get reversed, this matrix is recurrent. And in particular, when you apply mu white and mu black, you will always get back to your same original matrix. Every matrix we will work with in this talk is going to be recurrent. Any questions so far? Now the dynamics that we are going to consider is something that we call the bipartite belt. That's the sequence of mutations that is iterating mu white, mu black, mu white, mu black. And we can model this system with a dynamical system, which we call the T system. So the T system is just a series of values that we denote T sub I of t, and this is time t. So our time is moving. Every single mutation, time will increment. So this denotes the value of the ith cluster variable at time step t. And so our motivating question is, we already know what are the finite type cluster algebras, but when does this mutation sequence give finitely many cluster variables? So for finite type cluster algebras, we know the answer to when does an arbitrary mutation sequence give finitely many cluster variables. But we are focusing now on this specific bipartite belt mutation sequence. And this is what we call Zamolodchikov periodic. So if this mutation sequence is periodic, then we say it's Zamolodchikov periodic. So here's an example of an orientation of A2, and we will initialize it at time 0 and time 1. Now, as we mutate, we will increment with time. So we mutate at 1, mutate white, and we get a new cluster variable, and then we mutate black, we mutate white, we mutate black. So notice that originally our cluster variables were getting more complicated, but at some point they started to simplify again. And eventually we get back to our original cluster variables, but notice that they have sort of swapped positions. So if I did this another 5 times, I would actually get back to exactly the same cluster with the same orientation. So this is an example of a Zamolodchikov periodic cluster algebra. And this was an orientation of A2, which is a finite type cluster algebra. So notice that all of the finite type cluster algebras satisfy this condition because, of course, they are going to give finitely many cluster variables always. So for some brief history on this topic, in 1991, there was a physicist named Zamolodchikov, and he was studying these T-systems because they were thermodynamic Bethe ansatz equations. And so they were modeling the thermodynamics of a certain one-dimensional system. He observed that for specifically type A, type D, and type E, the system seemed to always be periodic. But he didn't know why. And so he posed this question. And since then, many of physicists attempted to solve this question. But the first people who were able to prove it was Fomin and Zelevinsky in their Annals paper in 2003, in classifying the finite type cluster algebras and then showing that those are Zamolodchikov periodic. Now, beyond just the Dynkin diagrams, let me also say that Fomin and Zelevinsky proved it not just for A, D, and E, but all of the other Dynkin diagrams, so the non-simply laced types as well. Now, beyond just the Dynkin diagrams, the question was, how far can we generalize it? Can we do this for pairs of Dynkin diagrams? What about tensor products? Those are still bipartite. All we need is something that's bipartite. And so Volkov was the first to prove it for the tensor product type A, tensor type A. And in 2013, Keller, in his Annals paper, proved it for all pairs of Dynkin diagrams, all tensor products of two Dynkin diagrams. Given this result, in 2019, my advisor, Pasha Galashin, and Pasha Pawlowski together used Keller's result to classify all quivers that satisfied this Zamolodchikov periodicity. So all bipartite quivers satisfying this periodicity. And so my result that I will explain today is the classification of all cluster algebras that are Zamolodchikov periodic. So this is a generalization of Galashin-Pawlowski's work to skew symmetrizable cases. And in fact, all of these cluster algebras are in natural bijection with pairs of commuting Cartan matrices. Now, recall that the finite type cluster algebras are in bijection with Cartan matrices, and this is a generalization, right? Like this is a larger class that includes the finite type cluster algebras, so it makes sense that we are taking now pairs of Cartan matrices. Any questions before we dive into the result?
So by Cartan matrices, you mean the finite types, right? Not just Cartan matrices of anything.
Yes, finite type Cartan matrices, but not necessarily reduced, not necessarily simply laced.
Thank you.
Are you gonna define Cartan matrices? Because I haven't
Oh,
heard
sorry,
of it.
I did not define a Cartan matrix. It will show up, Cartan matrices will show up, but for now you can think of them as the adjacency matrix for a skew symmetric. Yeah. So for the simply laced types, the Cartan matrix is essentially the adjacency matrix. Okay. So for people who don't remember Coxeter numbers or are not familiar, I've just put a table. Every Dynkin diagram has an associated Coxeter number that's very important in that root system. Now this is the same theorem as the last slide, but now I've given the actual period. So given a pair of commuting Cartan matrices, the associated T-system is going to satisfy this relation. If we go this many time steps into the future, we will always get back to where we started, where this is the Coxeter number associated to the first matrix, gamma, and this is the Coxeter number for delta. Now, because this is 2 times, h gamma plus h delta, there is always a notion of what happens at the half period. So if this is the period, the half period would be what happens at h gamma plus h delta. And this was my result from this February, that the T-system also satisfies this nice thing of, at the half period, we will always get a permutation of the cluster variables. And this is an automorphism of order at most 2. We saw this in our previous example with an orientation of A2, right? We did it several times, and eventually our 2 cluster variables swapped places. And if we did them again, they would swap places back. So that was our automorphism of order 2. So let's start with our main result. The general proof outline is going to consist of 3 steps. First, we are going to classify all pairs of commuting Cartan matrices, and then we are going to observe that all of these pairs can be obtained from quivers through 2 operations. And finally, we are going to show that periodicity is preserved under these 2 operations. So this will show one direction, probably the most important direction of this theorem. Okay, so first I have to define what this object is. This is a Dynkin diagram, which is an object I created, and this is just representing a pair of 2 matrices. So we say something is a Dynkin diagram if together they are bipartite and each component is a Dynkin diagram. So we can write it as in their matrix forms. We can also draw them in their Dynkin diagram components on the left. So here we have type D4 that's associated to this matrix right here, and then type G2 that's associated to this section right here, and they are connected by these blue components that are delta components. Now we say a Dynkin diagram is admissible if the associated Cartan matrices commute. So notice that these are not quite Cartan matrices, right? Cartan matrices always have 2s on the diagonal, but we can always naturally go between Cartan matrices and these adjacency matrices by just doing 2 times the identity minus the matrix. So notice that this condition, that the Cartan matrices commute, is equivalent to the adjacency matrices, gamma and delta commute. And we will just be focusing on that from now on because that is a very intuitive way of thinking about it. For the people that do cluster algebras, I will say that I did not just ignore all orientations. This is still a quiver. I'm just saying that red edges denote the orientation white to black, blue edges denote the orientation black to white, and we will leave it in their colored forms for the rest of this talk. So how can we tell whether something is admissible? Well, we are thinking about gamma and delta commuting, right? And these are adjacency matrices. So this is exactly the same as given 2 vertices, count the number of red-blue paths and count the number of blue-red paths. If these are the same number, for every pair of vertices, this is going to be admissible, right? Because a red-blue path is a gamma-delta path, and a blue-red path is a delta-gamma path, and every entry in that matrix is going to denote this number of paths. So for example, in this left-hand example, V1 and V2 are a non-admissible pair because there are 2 red-blue paths from V1 to V2, but there is only 1 blue-red path. On the other hand, this one is admissible if you take any pair of vertices, you can check that the number of blue-red paths is equal to the number of red-blue paths. But what about for a non-simply laced type? So even though this is not a regular edge, we can still view this as it's denoted in the adjacency matrix, in the Cartan matrix, as two arrows going up and one arrow going down. That's essentially what happens in the matrix. So given this, we can still see that these are not admissible because if I go from V2 to V1, I only have one red-blue path, but I have two blue-red paths. And so this cannot be admissible. On the other hand, this one is still admissible. You could check every pair, or you can just believe me. Any questions about admissibility? Okay. Now, a Dynkin bigram whose associated Cartan matrices are simply laced, we call an ADE bigraph. And this is something that was first studied in 2010 by Stembridge. Stembridge actually studied these objects because of their relation to Cosden-Lustig theory. He used them in their classification of certain Cosden-Lustig W cells. So in his work, he did classify all of the admissible ADE bigraphs, and these consist of 6 infinite families and 11 exceptional types. Here are 3 of them. This is the tensor product operation that I mentioned earlier. This is a tensor product of D4 with A3. And Golash and Polofsky used Stembridge's result to say that the Zamolodchikov periodic quivers are actually in natural bijection with these admissible ADE bigraphs. So these admissible ADE bigraphs are exactly the same as commuting Cartan matrices in the simply laced type. So this is the generalization. I classified all of the connected admissible non-ADE Dynkin biograms. This is the generalization of Stembridge's classification. You don't have to worry about all of these families. I will just show you what some of them look like. So this is type B that's bound with many copies of type A. We also have families of type D that's bound with copies of type C. And type E bound with copies of F4. So now that we have that classification, let's look at these 2 operations that will give us all of our families from quivers. The first operation is folding. Now, folding is a very natural operation for people in cluster algebras. It essentially, by definition, works optimally with mutation. And it was used in the classification, in Fomin and Zelvency's classification of finite type cluster algebras. So given a simply laced type, we can fold it to create a non-simply laced type. All we are doing is identifying vertices together through some automorphism of the graph. So here we've identified these 2 vertices together to fold Dn into Bn. Over here we have identified these 2 vertices, these 2 vertices, and these 2 vertices to fold type A into type C. E folds into F by sort of folding along the y-axis as well. And D4 can also fold into type G2 in this interesting way by actually identifying 3 vertices together. All 3 of these black vertices get identified together, fold up into G2. Now you can think of these arrows, these Dynkin arrows, as just a multiplier on the number of vertices that have been folded in. So I have written these in blue numbers. We can see that the pre-image had 2 vertices, 1, 1, 1. For type C, our preimage had 1, 2, 2, 2 vertices. Every single time our Dynkin arrow is going to denote a multiplier by 2 on the number of vertices. And for a triple arrow, that's a multiplier by 3. So since Fomin and Zelvinsky's classification, folding has become a very natural operation to use when you are thinking of going from simply laced type to non-simply laced type. So now that we have that, how can we fold our ADE bigraphs? We say that F is a folding automorphism if it restricts to a folding automorphism for every component. So here is an example. We can see we've got type D5 here and type A7 here in red. We are going to identify V1 and V1 prime. Basically, all of the VI and VI primes are going to be identified together. And we can see that type D5 does fold correctly into type B4, as well as this type A7 does fold into this type C4. And the only other thing we have to check is that do all of the other blue components fold in a good way also? And they do. We can see if we follow this line from V3 to V3 prime, what connects them is a component of A3 that does fold together into a double arrow here. We also have that again, another copy down here with the V4s that fold into a double arrow. So every single component gets folded with a valid folding automorphism, as we saw in the last slide, and this together forms a folding automorphism of the whole ADE bigraph. Now, we noticed after the classification, this is a corollary of the classification, that every single one of the admissible Dynkin bigrams can be obtained through folding or through what we call global flips, which is transpose, from an ADE bigraph. So here is an example. We have a simply laced Dynkin bigram here. Through folding, where we identify the V's and identify the U's, we get a new family. And when we apply transpose, we get a new family. So notice that applying transpose globally looks like we just flipped all Dynkin arrows. And actually, we can get every single family with this. One thing to note is that folding alone is insufficient. Folding, as I've mentioned, is a very nice operation that already commutes with cluster mutations. And so the fact that folding alone is insufficient is both surprising and disappointing because it makes the proof more complicated. We do need global flips, and this is not a nice operation in general for cluster algebras because they do not commute with cluster mutations. So using the global flips is the biggest factor in complicating this proof. So in order to prove that, these Dynkin bigrams are actually Zamolodchikov periodic, we needed this 5-way equivalence. So we really want to show that 1 is equivalent to 5. In order to show that, we need all of these arrows in between. And so they are all equivalent. We are not going to go through all of these arrows. What we are going to do is 1 to 4. Showing that the admissible Dynkin bigrams satisfy this tropical periodicity, which will end up being equivalent to regular periodicity. So this is number 3 in our 3-step process, proving that periodicity is preserved under our 2 operations. In order to do that, we need this idea of how to fold labelings. So we say that we have a F-symmetric labeling if when we apply F, the folding automorphism, it doesn't affect the value of the labeling. And given such a labeling, we can then fold it in such a way that we just take the same value. So let's look at this example This is an F-symmetric labeling. We've already talked about what F does, so I just need to make sure that, these two vertices have the same value, these two vertices have the same value, and so on and so forth. And once we fold this, we can see that we keep the same value. So this is an F-symmetric labeling and a valid folding of that labeling. Why am I using these labelings? It has all to do with the tropicalization. So you've already been given this exchange relation, which is what happens when we mutate a variable, a cluster variable. If I tropicalize it, multiplication becomes addition, addition becomes maximum in our case, and we get the same exchange relation, but slightly different. So why do we use tropical mutation? In many ways, it is easier to work with because in general, all you do is you pick real numbers for each cluster variable, and this is essentially tracking the dominant exponent of a specific variable because exponents follow these tropical operations. You can then you can set one variable equal to 1 and everything else equal to 0. And as you go through your mutation process, these values will give you how many times does this variable show up in every other cluster variable. So secretly, our labelings over here are the values for the tropical T-system. Now, this proposition says that folding and tropical mutation commute. As I said before, this is a completely unsurprising result. Folding and mutation will always commute. But what is surprising is what happens with the transpose and tropical mutation. So I've given on the left-hand side a single Dynkin diagram and its matrix, and the right-hand side what happens when I take the transpose. So we can see globally again, all of the arrows have been flipped. And these are the tropical T-systems moving with time if I initialize everything to be tracking only the second cluster variable. So if we just pause and look at this for a little bit, you'll notice that these two T-systems look very similar. In particular, the second column and the fourth column are the same for both, whereas the first column differs from the first column of this one by a factor of 3. And this fifth column differs from this fifth column by a factor of 2, right? Why could that possibly be? Well, notice if we look at our matrix right here, I have a skew symmetrizable matrix, correct? How do I make this skew symmetric? Well, I look at this, first of all, I've got a 3 here and a 1 here. So if I scale the first row by 3 and the last row by 2, I will get something that's skew symmetric. And that's exactly what's going on right here. We scale the first column by 3 and the second column by 2, and we get the other T-system. So that is our key. If we have a matrix and the vector of scalars that make that matrix skew symmetric, then our T-systems are related through exactly those scalars. And so because we can always get from one T-system to the other through this scaling, obviously if one of them is periodic, the other one will also be periodic. And so this periodicity is preserved under both folding and global flips. Given our previous results that all of our families can be obtained through these two operations, and that all of the Zamolodchikov periodic quivers are the admissible ADE biographs, these together give us all admissible Dynkin diagrams are Zamolodchikov periodic. And moreover, as I said in the beginning, the period is actually 2 times the sum of the Coxeter numbers. This, as a nod to Stumbridge, this classification also helps to classify the non-negative Kosten-Lustig W cells for products of two dihedral groups, which is a slight generalization of Stembridge's classification. Are there any questions about the classification before we move on to things unrelated?
So how do we get from the tropical periodicity to the usual one? So it looks like a big step in the, I don't know, upstream.
So yeah, the tropicalization, like tropical T system is, sorry, the periodicity of the tropical T system is exactly equivalent to the periodicity of the T system. One direction is obvious and one direction is not so obvious, but it actually is sufficient to show periodicity for initial labeling for like delta initial labelings, like 0, 1, 0, 0, 0. And this was something that my advisor did for the simply laced type originally. And it's not really that long, but I don't want to get into it. Other questions?
I have maybe two quick questions.
Yeah.
So this sequence of folding and flips, is this unique or not in general?
No, it's not unique.
Okay.
As in, like, you could do a different sequence to get the same family,
Okay.
potentially. Yeah.
And then, okay, and then my other question is, if you have a finite type cluster algebra, so you have an associated Cartan matrix, which is just the adjacency matrix, but by the fact that they're also Z periodic, you're guaranteed a pair of commuting Cartan matrices. What kind of pair could you write down?
Oh, for the regular Dynkin diagrams, yeah. You can view that as the tensor of a Dynkin diagram with A1. So it's
Oh,
just
okay,
the
yeah.
components are just single, like a single vertex. It's not really, it's sort of a trivial case.
Okay, cool.
Yeah.
Thank you.
Other questions? Okay. So from now on, we will just be talking a bit about half periodicity. Uh, this is related to maximal green sequences. I don't know if anyone here is familiar with maximal green sequences, but the idea is once we have our matrix, we can now frame it by adding a copy of the identity matrix. And this is adding n new vertices. We say that these new vertices are frozen, and what defines them is they cannot be mutated at. So let's just take an example of a quiver, and we're going to frame it. So we're going to see a new copy of every vertex with arrows going towards them, as denoted by our identity matrix here. Now we say a mutable vertex is green if it has only outgoing frozen arrows. So all of these, once we frame it, are going to be green. We always have green vertices to start with. Now a mutable vertex is red if it only has incoming frozen arrows. So all of these are green, but what happens when we mutate, let's do our same mutation. What we're going to see is with our new arrows, we get a new arrow from 1 to 2 prime, and this is going to reverse. So we can see that here. And suddenly our green vertex 2 has turned red. Notice that everything is colored, right? This is actually known as sign coherence. This was conjectured by Fomin Zelevinsky and proved by Gross, Hackenkiel, and Kontsevich that starting from the frame matrix and mutating in every possible sequence, every vertex will either be green or red. In other words, there will never be a combination of incoming and outgoing frozen arrows. Every vertex will either have one or the other. Now, given a mutation sequence, we say that it's green if every mutation happens at a green vertex. And a green sequence is maximal if after applying it, all of the mutable vertices are red. aka it's maximal because we cannot mutate anymore. We cannot extend our green sequence anymore. So here's an example of a green sequence. We started with our orientation of A2 that we framed. Everything starts green. If I mutate at 1, that turns that green vertex red, and I mutate at 2, now they are both red. So this is sort of the shortest maximal green sequence that could possibly exist with 2 mutations. But we also could have gotten there a different way. If we did the other mutation sequence, mutating at 2 first, we can see that we get this new quiver. If we mutate at 1, we get this quiver. Notice that when you mutate, sometimes red vertices can turn back to green, as we see right here. And so we have a longer maximal green sequence that eventually gets us to a quiver that is very similar to the quiver we ended with up here. And this is not a coincidence. For 2 maximal green sequences, we will always get to quivers that are isomorphic to each other. And they're isomorphic in a very specific way, which fixes our frozen vertices and, permutes our quiver. So this is called a frozen isomorphism, an isomorphism that fixes our frozen vertices, and is a property of all maximal green sequences. So my main proposition that I proved in February is that this bipartite belt is actually a maximal green sequence. If we do it starting with white, and we do this H gamma number of times, that's maximal green. And if we flip the ordering and do it H delta number of times, this is also maximal green. So notice that this is an orientation of A2. So as we said, this can be viewed as A2 tensor A1. The Coxeter number of A2 is 3. So we can see we have a length 3 sequence that's associated to the Coxeter number 3. Whereas the other Coxeter number is 2. That's the Coxeter number of A1. And we have a length 2 maximal green sequence. Yes, and in particular, these 2 outcomes are always going to be related via a frozen isomorphism. This will be very important in the proof of half periodicity. So how do we get to half periodicity? Just a brief outline. There are 2 lemmas that are going to be very important. The first one is known as the periodicity theorem. This was proved by Inu, Iyama, Keller, Kuniba, and Nakanishi. And it says that if we start with a framed matrix, okay, and we let B sub t be what happens at time step t, if when we mutate, we end up getting something that is frozen isomorphic to our original matrix, then the cluster variables will also follow that. So this is only true for our simply laced types. And this is a very overpowered theorem that offers an alternate proof to the periodicity conjecture. Now, notice that we already have this. From our maximal green sequences, we know that this is true for H gamma plus H delta. Because if we start with our outcomes that were frozen isomorphic, we work backwards, stitch together 2 maximal green sequences, that's going to be of length H gamma plus H delta. And so this will hold. Now, the other lemma is saying that this behavior for half periodicity is preserved under folding and transpose, which is a very simple statement for a non-trivial amount of work that does require some of the results from the classification. So together with these 2, you can see that, or it should be clear that half periodicity sort of falls out of both of these. And we actually know something more about that automorphism. When this sum is even, our permutation is actually bipartite color preserving. So white vertices will go to white vertices, black vertices will go to black vertices. Otherwise, it's color reversing. So let's take a look at this. An example where the sum of our Coxeter numbers is even. We can see the only thing that happened is that x8 and x9 switch places, so this is a color-preserving permutation. On the other hand, when we have an odd sum of Coxeter numbers, this is going to be color reversing. We can see that all of the variables on this side have basically switched with all of the variables on this side. Okay, so that is the end of half periodicity. Are there any questions? Okay, so some conjectures that I've been working on involve this idea of coloring mutations. So we have this idea of tropical mutation. Now, tropical mutation will either give us back this gamma component or this delta component, depending on which one is bigger. So we can color it red and call it gamma mutation if the max function gives us back the gamma component. And we also color it blue if that function will give us back the delta component. Now, something interesting happens when we color all mutations for one period. So recall that the number of roots in a root system is the Coxeter number times the number of vertices, aka the rank. Now, when we color all of the mutations in a single period, it turns out that the number of red mutations will end up being the number of roots in the gamma root systems. And the number of blue mutations is going to be the number of roots in the delta root systems. And this is something that is completely surprising and also a very nice result if it's proven, because this indicates there's some sort of bijection between the elements in the T system and the roots in the root systems. And this conjecture also holds if we sort of relax one of our constraints to say they don't actually have to be finite type. If we say that the gamma components are affine Dynkin diagrams, this conjecture still holds, right? All of the affine root systems have infinitely many roots, so this is no longer a periodic system. We just have a sea of infinitely many red mutations with some finite blue mutations that have been thrown in, which seem to correspond to the number of roots in the finite root system. Now, for the specific case of Dynkin diagrams, we were able to show that for a specific for a specific initial labeling, this conjecture holds true. And this used the half periodicity result from February. But we are unable to figure out how to prove it for the larger cases. In particular, it seems like there are regions where moving around in space, in the space of initial labelings, nothing will change, but at some point you would cross a wall in that space, and then some blue mutations would flip with some red mutations. So we can partition the space of initial labelings into chambers based on which sequence of colored mutations is produced. And we saw that for Dynkin diagrams of even rank, the corresponding fan ends up having C lambda distinct chambers, where this is the number of seeds in the cluster algebra. Conjecture 3, we actually believe that we may have solved this, but we need to check. Okay. And that's all I have for you.
Thank you so much, Ariana, for such a wonderful talk. Are there any questions?
Sorry, general question. Maybe I'm asking the wrong person because you've had an advisor, but where would one learn this kind of things nowadays? Because it's probably not in the Williamson Co book.
Oh, where would one learn about what in particular?
Well, everything after the Fomin-Zelevinsky papers, particularly the Pilevsky and Co and Galashin work.
If we're thinking about things related to the periodicity, Keller has Keller's Annals paper yeah, Keller's Enel's paper, the
Uh-huh.
periodicity conjecture, uh, Zamolodchikov's original paper. I guess that's not very helpful in learning about it. But Fomin and Zelewinski also have their paper, which talks about the finite type cluster algebras and in relation to periodicity, and that's why systems and generalized associahedra.
Mhm.
Those are the main ones.
Uh-huh. Thank you.
Yeah. Mhm.
Any other questions? I have maybe a really naive question. Do you expect any kind of meaningful notion of periodicity in the case of like larger tuples of Cartan matrices that don't necessarily pairwise commute, but some kind of like generalized notion of periodicity?
Um, yeah, so I've been asked this question before about like perhaps you could get larger tuples of Cartan matrices if we did like not bipartite coloring, but like tripartite coloring and things like this. And the only thing would be, I don't know how you would define the T system anymore, because all of this is sort of based off of originally the T system dynamics, which had already been predefined. Like, this is how you get to the next step in time. And so, how do you define the progression of time now when you don't have a single choice to make, like white and then black and then white and black? So it could be
Okay.
interesting. But I think my advisor tried to do it for the three case. He sort of did like a triangular grid, and he said it was
Mm-hmm.
not as nice as you would have wanted to be. And
Okay.
yeah,
Okay. Interesting. Thank you.
yeah.
Well, if there are no more questions, let's thank Ariana one more time. And I'll go ahead and stop the recording.